exothermic reactions. I knew about them before they were cool. You know, because like it's exothermic, so it's like taking the heat away, so then like it gets cold. That's right, today we're talking about heating and cooling curves. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu Chemin at ya. I'm your host Shu, and with me as always is Fu.
What up, nerds?
So Fu, in the last episode we compared the different phases of matter, talked about how phases and phase changes depended on temperature and pressure.
Yeah, and today we're going to talk about how those three phases of matter tie into energy. So let's get started. Heating and cooling curves, a lesson from the phases of matter unit. Heating curves. In a heating curve, a substance is heated at a constant rate from solid to liquid to gas. Heat is being absorbed, so it's endothermic. The temperature of the substance is measured as time passes. The resulting curved graph shows regions where the temperature increases and stays the same despite heat constantly being added.
We can't stress enough that there's a constant source of heat. So if you look at the diagram in the lower left, you're going to notice that there are regions on this heating curve where the temperature actually doesn't change. So it's a little confusing that we'd be constantly adding heat. And we'll talk about why later, but for right now, just remember, we're constantly adding heat. So imagine a Bunsen burner or a hot plate as pictured on the right, where we are constantly delivering heat to our substance. Wherever you see temperature, which is average kinetic energy, increasing, energy is being used to move the particles faster. So we're looking at regions A, B, C, D, or E, F. Wherever you see temperature constant, energy is being used to spread the particles out for a phase change. We're looking at regions B, C, or D, E. Let's focus in on the individual regions now. Let's say we're going from A to B. There's a solid present. The kinetic energy is increasing. We know this because the temperature is increasing, and that means the particles speed up. The potential energy stays the same because the particles are not spreading apart. So it's not like kinetic goes up and potential goes down like we've seen in other examples. That's because we're constantly adding heat. So there's a net influx of energy to our system, but just the kinetic energy is going up. The temperature at point B is called the melting point. And from B to C, we have both solid and liquid present. Now the temperature is staying the same, so the kinetic energy stays the same. This means the particles are moving at the same speed. However, the potential energy is increasing because the particles are spreading apart. Again, this is a phase change. All right, moving on to C to D. This is where we have only liquid present and the kinetic energy is increasing. Notice we have a sloped line. That means the temperature is going up, so kinetic energy increases. That means the particles speed up and are moving faster. The potential energy stays the same though because the particles are not spreading out. This is not a phase change along C to D. The temperature at point D is called the boiling point. So from D to E, we have both liquid and gas present. The kinetic energy stays the same. Notice it's flat, right? It's flat there. It's not changing for the temperature, and the particles are moving at the same speed. However, the potential energy is increasing because the particles are spreading apart. This is a phase change. You can associate flat region with phase change, flat phase change. Finally, we've got E to F. A gas is present, only a gas. The kinetic energy is increasing because the particles are speeding up, and the potential energy is staying the same because the particles are not spreading apart. Again, this is not a phase change. Okay, Fu, you're ready for some more dancing?
I am.
All right, this is the heating curve remix of the phases dance that you learned before.
Okay.
Okay, this is a little bit more complicated. You knew where to start,
all
good.
right.
All right, so we're gonna start at point A on our heating curve, right?
Okay.
So point A, we're a solid, our particles are together,
Gotcha.
We're vibrating. Let's say we're at a pretty low temperature though.
Okay.
So we're vibrating very slowly,
Okay.
low kinetic energy.
Got it.
Now, we're gonna start adding heat, and if we look along region A to B, you can see the temperature goes up.
Okay.
That means our kinetic energy is going up. So what does that look like?
Oh, so kinetic energy is motion, so the motion's going up. That must be moving faster.
Yeah, good, so we're gonna start to make this move faster. Now again, we're not spreading out the particles. Potential energy is staying the same, but kinetic energy is going up.
Okay.
Now eventually we hit B. Now this is the important part.
Gotcha.
Don't make them move faster from B to C. use your energy to just spread them out. So same speed, but now I start to separate my particles.
Oh, okay.
That's potential energy go up. When you spread out particles, your potential is going up. But they're moving at the same speed, so kinetic energy is the same.
Okay.
All right, so now we're gonna go along C to D. So temperature is going up, kinetic energy is going up. Again, we have vibrational and translational, but now we're gonna move a little faster this time as a liquid.
Okay.
So kinetic energy is going up. Potential is staying the same though, because I'm really not spreading out my particles anymore. There's no phase change.
Makes sense.
Now at D, I'm going to be at my boiling point.
Gotcha.
And again, same thing, move at the same speed, but this time we're gonna spread them out. We form a gas, the particles are completely spread out. And again, I used all my energy.
Okay.
For potential, the potential energy went up, the particles are spread out. Now we're at E to F. So now we're gonna take our gas, we're gonna increase the kinetic energy, we're gonna make them go faster.
That makes sense. All right, so we have a nice little animation here which shows you how those particle diagrams are related to this heating curve. If you take a look at the far left here, we got a solid represented in that particle diagram at the top, and that's where we have the solid phase of matter starting to heat up. It heats up until it hits its melting point, where it starts to melt from a solid to a liquid. We don't just change all the way from a solid to a liquid instantly, it takes some time. So you can see in the particle diagram, we have some solid, again, assuming this is water, because the solid is floating on the liquid phase there. Once we hit the liquid segment here, we have all liquid. All we're doing is using energy to heat that liquid up until we hit the next phase where it's gas and liquid together, where it starts to boil. We start to get some gas present. You can see in the particle diagram, you've got some gas and you've got some liquid at the bottom, until we finally hit the last part where it's all gas, and the gas in the particle diagram fills up the entire container.
All right, we're gonna go in the other direction now and talk about cooling curves. In a cooling curve, a substance is cooled at a constant rate from gas to liquid to solid. Since heat is being removed, this is an exothermic change. The temperature of the substance is measured as time passes. The resulting curved graph shows regions where the temperature decreases and stays the same despite heat constantly being removed.
So just like in our heating curve where heat was constantly being added from a Bunsen burner or a hot plate, in this situation in a cooling curve, heat is constantly being removed. So think of this as being in a freezer or some cold area where heat is constantly always being removed throughout the entire graph. All right, looking at our example of a cooling curve from A to B, it's just gas present. Kinetic energy decreases, which means the particles are slowing down. You can see that as temperature is decreasing. Potential energy stays the same because the particles are not getting any closer together. The temperature at point B is called the condensation point. So from B to C, gas and liquid are present. Kinetic energy stays the same. It's flat. Again, associate phonetically flat with phase change. Flat with phase change. Particles are moving at the same speed, so the potential energy then decreases because the particles are getting closer together. So from C to D, we have liquid present. Kinetic energy decreases. The particles are slowing down. Potential energy stays the same because the particles are not getting any closer together. The temperature at point E is again called the freezing point. E to F, liquid and solid are both present. Kinetic energy will stay the same, again, temperature staying the same, flat because we're going through a phase change. So the particles are moving at the same speed. Potential energy decreases, the particles are getting closer together. And then finally from F to G, it's just a solid present. Kinetic energy decreases. We can see again the sloped part of the graph, temperature is going down. The particles are slowing down, so potential energy stays the same, and the particles are not getting any closer together.
Note, the melting point equals the freezing point. It's the exact same temperature. Also, the boiling point equals the condensation point. Only the direction that we're going in varies. Also, you may have noticed on the previous picture of our cooling curve that there was kind of a strange region in there where it sort of dipped below the freezing point. Well, when a liquid cools below its freezing point but doesn't freeze, it is called supercooling. And supercooling occurs only when there are no impurities in the liquid from which crystals can form and grow. Those are called nucleation sites. So this would work best with a distilled water bottle you left out in your car, and you come back and it's still liquid water even though it's the middle of winter and it's freezing cold out, but then you like shake it or disturb it and then it just instantly freezes. And that's due to supercooling, that it didn't freeze initially, but then when you disrupt it, it goes ahead and freezes.
Calculating heat for phase changes. So along any region in which the temperature changes, those ones were A to B, C to D, or E to F, the heat absorbed or released is calculated using Q equals MC delta T. This again is found on table T of your reference tables. Remember that the value of C is 4.18 joules per gram degree Celsius for water. This is also found on table B. For a heating curve, delta T is positive and Q is positive. This is endothermic. For a cooling curve, delta T is negative and Q is negative. This will be exothermic.
Along regions where the temperature is constant, that would be B to C and D to E, you will use Q equals MHF for melting or freezing and Q equals MHV for vaporization or condensation. HF in that formula, Q equals MHF, stands for the heat of fusion. It's the amount of heat required to completely melt 1 gram of a solid, and it's 334 joules per gram for water specifically. This is found on table B. HV from the formula Q equals MHV stands for the heat of vaporization. This is the amount of heat required to completely vaporize 1 gram of liquid. It's 2,260 joules per gram for water, found on table B.
Notice how the heat of vaporization is much greater than the heat of fusion for water? This is due to more energy being required to completely separate the particles in the liquid phase to enter the gas phase than is needed to only slightly separate the particles in the solid phase to enter the liquid phase.
Let's talk about a secret dance move hidden within the remix of the phases stance. I'm not even gonna deal with Fuqua right now. He could not handle this. Heat of fusion, heat of vaporization. Are you ready? All right. Solid to liquid. Did you see that? Did you see that? Just a slight separation of the particles. That's heat of fusion. But now let's do heat of vaporization. We're gonna go from liquid to gas. Did you see how I completely separated those particles? So it's gonna take a lot more energy to do this than to do this. So the heat of vaporization is a much higher value than the heat of fusion.
All right, ladies and gentlemen, we're gonna do an example of a phase change heat calculation. Shu, are you ready?
Yes, I am.
All right, if 25.4 grams of steam is condensed, how many joules of energy are released by the water? So like all calculations we've been doing this year, if we're gonna use a formula, we're gonna use the steps FSA. So for F, we're gonna figure out our formula here. So we have a few choices on table T. What do we have as clues in our question that might tell us which formula to use?
All right, well, I don't see any sort of temperature change, so I don't think it's Q equals MC delta T. In terms of the phase changes, I see that I've got steam and it's condensed. Fusion is solid to liquid and vaporization is liquid to gas, so I don't know, I'm not sure with steam is condensed.
Yeah, there's no word like vaporized here, right? But condensed is the opposite of one of those, actually. So what is condensation the opposite of?
So condensation is gas to liquid, so that would be the opposite of vaporization.
Okay, so then which formula are we going to use?
Well, I guess we have to use Q equals MHV.
Good. Now we can use that just because it is the exact opposite of vaporization.
Okay.
All right. So when we're doing FSA, we want to, once we get our formula, circle the variable we're solving for. So what is the question asking for?
Well, it says how many joules of energy are released,
All right. Now you can use table T because it says what all these variables are for, but which one represents joules of energy?
Yeah, joules of energy would have to be Q. That's what I'm solving for.
All right, good. So we should have the other two variables. So does the question give us one of those?
Well, I definitely have mass here. It's 25.4 grams.
Good. Does the question give us the H of V value?
No, but that's a constant, right?
It is.
So I got to go all the way back to table B for those constants for water, right?
Good. So what is the HV sub-value on table B for water?
Well, it's 2,260 joules per gram.
All right. Again, this is the heat of vaporization. We're not vaporizing though, right? We're kind of doing the opposite of vaporization. So we want to show that mathematically. It's a simple fix. What are we going to do?
Well, since, and it says the energy's released, so I think this should be negative.
Good, and if it's negative, it's exothermic. That's good to know.
All right, note, exothermic. All right, I think I'm ready to solve now.
I think so.
All right, so I just multiply those two values. It looks like 3 sig figs, no matter how I look at it, but really, I would just look at the number given in the problem. Good,
and remember, sig figs are for measurements, they're not for constants. So since HV is a constant, we wouldn't look at that. We just look at our measurement, which is grams here of 25.4.
So negative, it's gotta be negative, 57,400 joules off my calculator. And that should be it.
Good job. You try. If 167,000 joules are required to melt a block of ice, what is the mass of ice? Remember to do all work, FSA. Circle what you're solving for. Your answer should be in proper units and significant figures.
Well, that's gonna do it for today's episode on heating and cooling curves.
Later, nerds.
Today's episode is brought to you by
Henri Remulaz, cheese printer. To create beautiful meals for your family, just say cheese. Say cheese cookbook included.
But we never off, always on till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie like my homies, boys to men. It's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.